This screencast will finish the chapter. We're going to look at some related but somewhat independent chunks of concepts having to do with waves. We begin with 13.6, something called a damped oscillation. Here we're using the word damped not to mean wet or anything like that. We mean that when a wave is traveling through a medium, because of friction and the loss of mechanical energy as a result, the amplitude of that wave gets less and less and less. A good example of a practical application of this would be shock absorbers in a car. When you go over a bump, you want to have some of that bump absorbed so that you don't hurt your back or your neck. But at the same time, you don't want to keep bouncing up and down for the next several blocks. So if we look over here in the next page, you have a diagram that shows you that some shock absorbers use oil or some other thick, gooey liquid in order to absorb the energy when you go over a pothole. And some shocks use an actual physical spring, and then some shocks use a combination of both, a viscous fluid and the spring. Now, this picture over here is a great example of damping where the amplitude becomes less and less over time. So here along your x-axis is time, and you can see your amplitude to start with is quite large, and then it gets smaller and smaller and smaller as the energy is absorbed and lost until eventually you have no wave at all. As far as shock absorbers are concerned, we want to build and construct and then calibrate that shock absorber to be just right. The possible conditions would be to be underdamped, pictured right here, in which case you can see when it's underdamped, it bounces a bunch of times, or to be critically damped, which is the one in the middle, which in less than one complete vibration, the energy is all absorbed and you never actually quite get back to your equilibrium point. And then very or over damped is this one right over here, which basically is different from the critically damped one in that it takes an awful lot longer before it approaches the x-axis. Now, as far as shock absorbers are concerned, we like to be slightly underdamped. In other words, we probably don't want to bounce one down and up more than about one, maybe 1.5 times when we go over a bump. Next, there are all kinds of waves in creation, in nature, that we can study. We will be studying sound waves in the next chapter. Right now, we're studying waves on a string. In earth science, we might study seismic waves from an earthquake. And then in later chapters, we're going to talk about electromagnetic waves, part of the electromagnetic spectrum, which would include visible light, radio, television, X-ray, gamma, UV, all of the ultraviolet, all of those kinds of waves. And we're going to find there's a really cool equation that relates the velocity of any one of these waves to its frequency and its wavelength, and we'll get to that in a minute. This will be what we'll be talking about over the next several chapters. So what is a wave? It's going to be a disturbance, not a disturbance in the force from Star Wars, but a disturbance in a medium. But you can also have waves like electromagnetic waves that don't even require a medium to disturb. They can go through outer space. And so as far as waves that travel through a medium or a material, it could be water, it could be a string or a rope or a wire, all kinds of material, or oil. It could be all kinds of materials that the wave is going to go through. And as that wave representing energy goes through the material, it disturbs it in a somewhat predictable way. And it can create, for example, crests and troughs, or compressions and rarefactions, which we'll be talking about in a minute as well. So we can consider a wave to be a motion of the disturbance. The wave is going to go in a particular direction. The medium actually does not travel with the wave. The medium is not like a surfer traveling with the wave, but the medium is just going to go up and down as the wave goes through it. We are focusing right now on mechanical waves, waves that have some source of disturbance, waves that are going to be basically disturbing a medium that it's going to be traveling through, and then we're going to be assuming some physical connection or mechanism through which the adjacent portions of the medium can influence each other. In other words, the particles that make up the medium can affect the other particles that are adjacent to it. Now, there are different kinds of waves, and this will be demonstrated in class. Some waves, when they travel through a medium, distort or disturb the wave perpendicularly from the direction of motion. For example, the wave in the picture over here, the wave might be traveling this way, but the disturbance is going up and down this way. We call that a transverse wave. Then you can also have longitudinal waves, and longitudinal waves will be a wave where we have compressions and the opposite of compressions called a rarefaction, where the material might be squeezed together and then spread apart and then squeezed together. Compression right here, rarefaction, compression. Sound is the best example of this. This would be a longitudinal wave. And that is one of your test questions, by the way. So a transverse wave, the motion is this way of the disturbance, but the wave travels in this picture from left to right. And in this particular wave, the second one, the wave is going to go down this direction. If there's a barrier, it's going to bounce off the other end. But as it travels in one way, the disturbance is also in the same direction. You can have a compression, another compression. You can have a place where it's spread out, which is called a rarefaction. Now, it is possible in some unusual circumstances to have just a single pulse, a single wave. And I'll let you read this interesting story about the Scottish engineer, John Scott Russell, who almost 200 years ago discovered a solitary wave that was moving in front of a barge, just a single pulse, maybe when the barge was put down in the water or something happened, and it produced a single pulse that traveled through the water in front of the barge, and Russell jumped on a horse and traveled at about 10 miles per hour until he just couldn't get to it anymore. He either couldn't keep up with it, or else he was no longer had a path to gallop the horse along while following this wave. Practical applications are in particle physics and astrophysics. So we already mentioned that when a wave goes up, we call that a crest. When a wave dips down, we call that a trough. We also talked about compressions and rarefactions for longitudinal waves. We're also going to mention torsional waves when this is demonstrated in class. Electromagnetic waves are waves that we can talk about a crest and a trough, transverse waves. Waves traveling along a rod or a wire or a string can be transverse waves as well. In a compressional wave, the compression is actually a region of high density, and the compression is a region of low density. Now, if we have an object that's moving a wave up and down, and these waves are traveling to the right, you'll notice that any particle, picture a particle, or maybe a Sharpie ink point on a rubber band or something elastic right there. That's simply going to go up and down as the wave goes from left to right. It's going to go up and down. It oscillates. It's a vertical oscillator. Now, when we talk about how many times per second these waves travel, it depends, of course, if we're talking about waves traveling along a wire or a rope, waves traveling through the air, which would be sound, but also sound waves that you can't hear because they're too low or too high, infrasonic or ultrasonic. It can also be, those waves, I should say, are between 20 vibrations per second and 20,000 vibrations per second when we talk about the range of optimal human hearing. This will be demonstrated in class as well. The maximum displacement is called the amplitude, a vocabulary word you should know. And then when we relate the wavelength to the frequency and the speed of the wave, and again, speed of the wave in this case is not the speed going up and down, but the speed going from left to right. That's called the wave speed. And that is represented by this equation right here, which is an equation worth memorizing, even though that would be given to you on an AP test. And this shows that velocity equals the frequency and the wavelength. Frequency and wavelength are inversely proportional to each other. Sometimes instead of the letter F for frequency, you'll see the Greek symbol nu, N-U, for frequency. But that looks a little bit too much like velocity. Velocity, we often write it with a little tag off the right side of the V. And then this symbol right here that looks like an upside down letter Y is called lambda in the Greek language. So lambda would be a Greek symbol and nu would be a Greek letter of the alphabet. The math problems using this equation are quite simple, and I'm not going to spend any time going over them. Now, how fast does a wave travel on a string or a wire? This is what we mean by a wave speed, not the vibration up and down, but the speed along the length of the medium that the wave is traveling. And if that medium is a wire or some material like that, it turns out that that speed is obviously proportional to the tension. Here, F stands for the tension in the wire. And you all know from guitars and pianos and so forth, if you increase the tension, you're going to get a higher pitch. So when I think about pitch, and we'll talk about this more in the next chapter, I'll make my voice go to a higher pitch, and now it's a real high pitch. And then when you're through laughing, I can go to a deeper and lower pitch, bass versus tenor. And the other thing, it's inversely proportional to something we call mu. And mu is the linear density. Here's another Greek letter. Mu, you've already seen it as the coefficient of coefficient of friction. This is a different use altogether. And linear density is the mass per unit length. So obviously, if you stretch the wire, the mass is going to be a little bit less in that same length than if the wire is somewhat compressed. And so in either case, whether you increase the tension, which is going to increase the stretch, or if you use a thicker wire as opposed to a thinner wire, you're going to change the speed in which the wave travels down that wire. So that speed depends upon the properties of the string or the wire. I meant to say I think I just erased the word. There it is, the word properties. There we go. Now, I just said that we can increase the speed of a wave on a stretched string by increasing the tension, here represented by the force applied to the string or the wire, now designated F sub t, as opposed to just the letter T. And of course, we can increase the mass of the string if we wrap it in metal. So in a classical guitar, the 2 or 3 lower strings will be wrapped in wire so that they have, you can hit the lower notes in a chord. Waves can also interfere with each other. when one wave strikes another wave, they don't knock each other out, but they don't smash into each other and fall apart. They travel through each other, which is pretty remarkable. We're going to be talking about interference patterns in a later chapter, especially as it refers to light. But when two waves are in the same medium at the same time, we can predict what the actual wave will look like, what the resulting wave will be, using the principle of superposition. And basically, when we add those two waves together, we are adding up their amplitudes or displacement. So, for example, in this picture down here, if I have wave A and wave B in the same medium at the same time with this configuration, I would add this amplitude to get this amplitude. And I would add this amplitude to this amplitude to get this amplitude, and everywhere in between. And this will be demonstrated with more complicated waves in class. When crests line up with crests, we say they're in phase, and you get constructive interference. When crests and troughs come together, they have a tendency to cancel each other out, and we call that destructive interference. Cancellation would be destructive. Cancellation. Constructive interference is when they reinforce each other. And the result is bigger than each of the parts. Now, next we see that there are, here's some examples of a small wave and a big wave coming together. In other words, when you get interference, the two waves do not have to be the same amplitude. And then you're going to get all kinds of more complicated shapes, like you see in these pictures here, with partial cancellation and partial reinforcement. And then when the waves separate, it's like they never even met. They go right through each other and continue on their merry way until, of course, friction takes its toll and the energy is dissipated. Another interesting thing about waves is that they can reflect off of surfaces, and we'll talk more about reflection with electromagnetic waves as well in a later chapter. But when a wave travels in the direction of a barrier and to a fixed point that cannot oscillate or move, when that wave strikes that barrier, the barrier pushes back. And so the wave might come in as a crest, and then it gets pushed into a trough going back the other direction. So it gets inverted. The reflected pulse is inverted when it strikes a fixed solid barrier, which is very different in this case when your incoming wave traveling to the right strikes or enters a area that it isn't fixed. And here it's a ring that is able to loosely, frictionlessly move up and down the rod that it's around. And as a result, when you get a crest coming in, you get a crest coming out. And so that's very, very different than when a wave strikes a fixed barrier. Now, if you wonder what a practical application of that is going to be, the more practical applications would be when we talk about electromagnetic waves in the unit on light and optics. And except for the demonstrations that will be in class, that concludes Chapter 13.